Welcome to the deep dive. So, today we've got something, well, a little unusual for our source material.
Yeah, we're not digging through a quarterly report or a white paper this time. We're diving into an audio recording of an actual first-day lab session.
Specifically, the Electronic Design Workshop, or EDW, conducted by Dr. Dhananjay V. Gadre.
That's right. And our mission here isn't really to learn how to solder. It's to pull out the core philosophy he's teaching, which is all about, how to think critically and learn for real when technology just gives you infinite shortcuts.
Okay, let's unpack that, because Dr. Gadre wastes absolutely no time. He jumps straight into what he sees as the biggest threat to learning today.
The AI trap. It's this pattern he describes, and it's so common. A student gets a problem, they feed it to an AI, get a solution.
And just forward it on. They become a passive courier, not a creator.
Exactly. The AI becomes this uncritical middleman, and the student completely skips the hard part, actual learning. The real loser in that whole transaction is the learner themselves.
But is this just a theoretical problem? I mean, does it have real, tangible costs?
Oh, it has immediate and, frankly, embarrassing costs. He told this story about getting a certificate of gratitude from a school where he gave a lecture.
Okay.
The certificate was signed by the head of school, but it was missing the letter T from his own name. It just said Dhananjay.
Wait, the principal signed a formal document with their own name spelled wrong.
Their own name. That's what I'm saying. It's just a perfect small-scale example of a total failure of oversight.
So who's responsible for that? Not the template or the AI they probably used.
Precisely. It's the person who signed it, the person who submitted the output. If they'd just taken a second to apply that critical check the way you would before signing a check, they would have caught it.
And he really raises the stakes on that point, right? He uses that mythological story of Lord Shiva and Bhasmasura.
He does. Granting this incredible power without oversight almost led to his own destruction. The message is just so clear. If you produce an output, you own the garbage.
So what's the way out? Don't use the tools.
No, not at all. He says use the tools, but you have to be able to defend and explain what they produce. If you truly understand it, the teacher's goal is met. It doesn't matter how you got there.
That distinction is everything. But, there's a bigger, almost invisible cost he brought up that really floored me. The environmental footprint of all this.
It's a staggering figure. He mentioned that a single, really complex ChatGPT query can use the same amount of energy it would take to power 100 homes for a year.
One query, 100 homes for a year.
Yes. And when you connect that to the macro problem he's describing, people using AI to write reports, other people using AI to summarize those reports, you realize you're in a loop where no one is actually reading anything.
And you're burning incredible amounts of energy to generate information that might never even be verified by a human.
The oversight isn't just about learning. It's an environmental and intellectual imperative. It's a huge deal.
That really sets the stage. So moving from that philosophy to the very practical side of things, the job market, where does this leave people?
This is where it gets really interesting. He brings in this candid warning from an alumnus of NSIT.
A warning about what, exactly?
A huge one for computer science students. The source is clear. AI is going to seriously disrupt, maybe even eliminate, a lot of traditional CS jobs, especially for the students who are just completely obsessed with DSA.
Data structures and algorithms.
Yeah.
But that's like the bedrock of software engineering. Why would that make them vulnerable?
Because it's about where that knowledge meets physical reality. AI is getting incredibly good at abstract, algorithmic problems. But the argument is that electronic students are actually in a better spot because of the convergence of digital and physical.
Explain that convergence. What does that mean here?
Well, he points out that something like 99% of modern electronics need programming. You've got embedded code, cloud code, the whole stack. And who's best to write that low-level stuff, the code that actually touches the silicon?
The person who understands the hardware?
Right, the electronics grad. They get the registers, the timing constraints. A lot of CS people struggle when the code has to deal with the messy physics of the real world.
So that's the lifeline. That's why they should feel lucky.
Yeah.
But getting that edge means you can't take shortcuts.
Exactly. And he gives two pieces of very blunt advice. First, he says, stop talking to average seniors. If you only get advice from the middle of the Gaussian curve, you'll only ever be average.
And a second piece of advice.
Avoid the ChatGPT of hardware. He talks about these shops, in places like the district center, that will just build your class projects for you for a fee.
So you're just buying the output again.
You're buying the output. You get a finished project, but you have zero learning, zero experience, and you can't explain a single thing about how it works. It completely defeats the purpose.
And that purpose, that hands-on building, it leads right into the next big thing from the lab. This huge convergence happening between low-power electronics and high-power electrical engineering.
Yeah, the lines are just completely dissolving. And the best example he gives is the shift to electric vehicles.
He talked about the voltage standards. Old systems, like rickshaws, might run on 12 volts, but modern EVs are at 400 volts.
And they're not stopping there. Companies like Tesla and BYD are pushing hard for 800-volt architectures.
So the question is why? Why go to such high voltages? It seems more dangerous.
It's all about efficiency and cost. It comes down to that fundamental equation. Power equals voltage times current. P equals VI.
Right, so if you want to keep the power output, P, the same, but you use a low voltage V.
Then your current, I thought, has to go way, way up. It just skyrockets.
And high current is bad. That's where you get all the heat loss.
Catastrophic heat loss. The energy loss is I squared R. So if you have a huge current, the waste is enormous. To fight that, you need incredibly thick, heavy, and very expensive copper wires.
But if you double the voltage to 800 V, you can cut the current in half for the same power.
Exactly. And that means you can use thinner, lighter, cheaper wires. It saves weight, it saves money, it increases range. The physics just makes it a no-brainer.
What's really wild is that this isn't just for cars. He said data centers are adopting this standard.
Immediately. AWS, Google, Microsoft, they're all running their backbone power distribution at 400 or 800 volts.
But don't CPUs run on, like, less than 1 volt?
They do, but they use the high voltage to move the power across the huge server farms with minimal loss, and then they step it down right at the server rack to the tiny voltage the chips need.
So an electronics engineer today has to understand high-power systems that used to be a completely different specialty.
The walls are gone, completely.
Which brings us back to the workshop itself. The structure of the course is designed to build that physical knowledge, right?
Absolutely. He said it's double the lab hours compared to theory. It's all about emphasizing the hands-on building.
And they start with the absolute basics, like literally a piece of wire.
The wire itself, and there's so much to it. You've got different insulators like common PVC versus expensive Teflon for high heat situations, and then there's enameled wire.
That's the stuff in motors, right, with the coating that looks like nail polish.
Yeah, that thin coating is the insulation. They also covered wire gauges, the SWG system, which is always counterintuitive. The bigger the number, the thinner the wire.
He also mentioned stranded wires for redundancy.
Right. It's not just for flexibility. If one of those little strands breaks, the others can still carry the current. It's a simple, robust design.
And from there, they went to fuses. I like the bit about the resettable fuses.
Those are so practical. They trip when there's an overcurrent, but then they just cool down and reset. They're often what's protecting the USB ports on your laptop.
And then into semiconductors. He mentioned MOSFETs, BJTs, and then the really high-power stuff.
The SCRs and triacs. The triacs is a great example because it's in all our modern fan regulator.
How does that work? What makes it better than the old ones that got really hot?
Those old ones were just big resistors. They literally burned off the extra power as heat. A triac is a switch. It just chops up the AC power wave, only letting a little piece of it through to the motor so it controls the speed without all that wasted energy.
That's a great physical solution. But the deepest lessons seem to come from the experiments on just one single component, the resistor.
Totally. He held up this big white ceramic resistor, a 50-watt, 5-ohm resistor. And the point was that its size has nothing to do with the 5 ohms.
It's all about the 50 watts, the power it can safely dissipate.
Exactly. He said you could hook it up and use it as a little portable heater because it's built to handle that much power. It's such a tangible link between a number on a spec sheet and a physical reality.
Then came the first experiment. They measured a resistor, then heated it up with a soldering iron.
Right, and you'd normally expect the resistance to go up with heat. That's what most conductors do. They have a positive temperature coefficient, or PTC.
But that's not what happened.
No. They watched the multimeter, and the value started to drop. It went from around 9.96 kiloohms down to 8.9 K.
So it has a negative temperature coefficient in TC.
Precisely. Resistance goes down as temperature goes up, and that property is exactly what you use to make a temperature sensor. That's what a thermistor is, a resistor designed to do that predictably.
The second experiment seemed even more fundamental. He actually physically changed the resistor.
Yeah, he took a watchmaker's file, a really fine tool, and just carefully started scraping the resistive coating off the side of it.
And what happened on the multimeter?
The value started to climb instantly. It went from 9.92K up to 10.22K. It was a perfect demonstration of the physics resistance is inversely proportional to the cross-sectional area. As he filed away the area, the resistance went up.
And this is actually a real manufacturing technique.
It is. If you need a super precise resistor value, you can start with one that's a little bit low and then laser trim it or file it up to the exact value you need. Then you just put some enamel paint over the spot to protect it.
It's just a perfect example of how doing something with your hands teaches you the physics in a way a simulation never could.
And that leads to the final step, the documentation. He made them record the date, 2026-0102, and that exact final value, 10.22 kiloohms.
It's training them to act like scientists, right? Create a verifiable record of what you did.
That's the core of the discipline. You make a change, you record it, and you come back later to verify it's stable.
And he left them with some homework that anyone listening could actually try.
2 great projects. The first is to take 1,000 resistors and actually measure every single one, then plot the values in Python to see the Gaussian curve, to check if the manufacturer's 5% tolerance is actually real.
That's a cool intersection of hardware and data science.
It is. And the second one is even simpler. Just draw a thick, uniform line with a graphite pencil and measure the resistance every centimeter to prove the relationship between resistance and length.
So when you pull this all together, what's the big lesson from this one deep dive? It seems so clear that real learning, the kind that makes you valuable, isn't about the shortcut.
It's about the oversight. It's about getting your hands dirty and understanding the why, whether you're managing an 800-volt system or just filing a 10-cent resistor.
And we have to keep coming back to those hidden costs. That idea of a single query powering 100 homes for a year. It forces you to think about the energy we're burning.
Information isn't free. It has a real environmental footprint. Our rush for answers has to be balanced with a real commitment to scrutiny, to not waste cognitive or literal energy.
A really critical point. And speaking of physical consequences, he recorded that filed resistor at 10.22 kiloohms. But if that little spot he filed wasn't perfectly sealed with enamel paint, will humidity or corrosion in the air change that value over the next week? That permanent change might not be so permanent after all. Something for you to think about.